All right, I'll go ahead and get things started here, everyone. Good afternoon or good morning, depending on what time zone you're in. Before I get things started, I'm going to go ahead and start a poll for the audience, just to get a little bit of information. Um, and so while you have a chance to look at that, I'll introduce myself. I am Fletcher Turner, the newest electrical applications engineer at TrueInsight. And today we're going to be looking at Altair Compose and a couple of applications here. So um, we're looking at process automation as an umbrella term, but there's a lot more to Compose than just that. And we're going to look at some of the different capabilities and functions of this software. If you have any questions throughout this webinar, you can go ahead and post them in the Q&A chat. I've got a colleague on the call with me who will be supervising that throughout the call and answering any questions you might have. And we can take some time at the end for me to answer anything left over or anything that we need to take a deeper look at. So we'll go ahead and take a look at what we're going to do today. So first I'll give a brief overview of what Compose actually is at a high level, what would be on the cereal box when it comes to Compose. And then we'll look at some applications and demos of some of the key features within the software. Things like simple calculations and calculation sweeps. And one of the really cool things in Compose is the ability to create a graphical user interface. There's actually a nice GUI within Compose to build your custom GUI, so that's nice. And then we'll take a look at some more complex calculations that the software can handle. And then we'll wrap up with how it can be used with some other tools, and then we'll address any remaining questions. So to start us off, what exactly is Compose? So from a 30,000-foot view, it's a code-based engineering environment utilizing OML, Open Matrix language, which is like many other languages. Programming languages. It's good for calculation, scripting, and data visualization. And it's got an extensive library of mathematical operators and functions for all sorts of numerical computations that might be of interest to a wide range of engineers. I know I myself am an electrical engineer, so some of the examples I'm showing are kind of electric-centric, but there should be some valuable information to pull from that where you can apply it elsewhere in other fields. And the fact that it is an OML means it's really good with working with very large sets of data. And that could be data from, like I mentioned earlier, other Altair products. So since it is built around matrices, it can handle a lot of information much faster than say Python might be able to. But it is worth pointing out that there is a Python IDE within Compose. So we'll start off with some various calculations available to you within Compose. So I hate saying this because it makes it sound like I'm almost insulting the software by saying that at its simplest it's a calculator. So while that's not all Compose can do, that is true that if you type in 2 + 2, you will get 4. But you can then ramp up to much higher orders of magnitude and complexity and start modeling or calculating whatever it is you might be interested in. And again, like other OMLs and many other languages, the variable declaration is a handy feature, not unique to Compose, but it's still really nice to have that when it comes to creating something unique to your application. And those can be, any kind of number or text or matrices of other variables, which is really nice. And then again, it being an OML, it's very strong in vectorization. So a lot of times you might be interested in looping, but we can speed that up, do calculations more efficiently with vectorization of McKenna standard for loop or while loop. And then, of course, any of this data, you can visualize it in 2D or 3D, depending on what your needs are. And there's some powerful tools available there to take a look at that. So I'll go ahead and pull up a couple of just simple examples to show kind of what the interface of Compose looks like. So we've got our script editor right here in the middle. This is where we can actually type our code and start saving variables and telling the program what we want it to do. Down here, we've got our OML editor, which is good for quick changes, quick calculations. You don't have to actually write a script up here. You can just do something like, like I mentioned, my 2 + 2 example, and we'll get 4. And then we can clear out any variables we have and clear that console. So you noticed, and I'll point it out again later when there's variables in it again, this variable browser down in the bottom left, that's where anything that you have saved you can actually look at. So if you are calculating something and you have intermediate steps, or you're interested in looking at a matrix, you can just click on that and you can pull that information right up and take a deeper look at what information you're saving. And then another thing that's interesting, just in the general use of it, is you can look at your file browser, so you can see what files are within the current directory that you're working in. So if you are referencing some other output file of some other software, you can make sure that you have the right file path. Or it's within the same folder, and you don't have to type a long file path, and you can just reference the file directly, just checking that it's in the same folder. So I'll go ahead and take a look at a couple of simple calculations and features within Compose. So this first one, it's just a simple curve fit. So I always like to start my scripts off with these 3 commands. They're not really necessary depending on your workflow, but you already saw me type in a couple of them in the OML window. So that's the nice thing, is they'll work in script and down here. Most commands will. And so you can say this CLC clears the console, clear all, clears our all stored data, including variables, and close all would close any figures that we have open. So this is just some random data right here. This is actually from an old place I worked a couple of years ago that had a bonus structure where work was assigned a certain amount of points, and then you got at the end of the project term, you got some dollar value in return for those points. I couldn't remember the actual points, so I made up some data. But here you can see again, we don't have to type out 1 through 20. We can just do 1 in increments of 1 up to 20, and then some bonus values that maybe aren't as linear. So what I've done is I just used the scatter function, which will just drop them all in a Cartesian grid. And then I've defined a polynomial fit. Right now it's 4th order. Let's take a look at a 2nd order polynomial fit. And then we'll plug in our points and see what kind of line we get on the output. So if I just run this, you can see our blue dots are those input points we got from the scatter, and then this green line is that a polynomial regression model that we just created. And you can see our root mean squared error and our mean squared error are both not that good, and you can see that this doesn't fit the data very well, but we can just increase the order of this right here pretty quickly, get closer. I'm going to do it one more time, and we see that now we've got a pretty good fit of our data. So again, this is a small data set and almost a trivial example, but it's nice to show just some of the capabilities with some of the pre-built functions within Compose. So again, we're not just limited to 2D plots. We can also take a look at some 3D plots. So I'm gonna go ahead and close that right there. So what I've done here is just defined some X and Y points. I'm going from 0 to 10 with a pretty small scale of 0.01. And then just defining a variable to store those outputs as Z. So just a simple three-dimensional a function right here, two inputs. And so I've done it two ways. I touched on looping versus vectorization. So the first way I've done it is actually a nested for loop where we go through each individual combination of inputs from X and Y to calculate the corresponding Z output. And then I've plotted it right here. Since it's really fine, I cut the mesh lines off because it just looks like a black blob if I leave them on. But then I've also done it down here where I've vectorized my Y input and just looped through the X input. So let's go ahead and just run this and see what we get. So you can see this is our plot right here. Since it is a really fine mesh, it is a little laggy on moving it around on my machine, but we could make that a coarser mesh and we wouldn't have that problem. And you can see down here just the benefit of vectorization. Even though the first one was still less than a second, you can see that drop in time right there. We can actually, using our command window down here, we can see how much faster. We can see that it's about 68 times faster, just that one little change. So you could imagine the kind of effect that this would have on larger sets of data, being able to manipulate them much faster. And you can see that we got this Z output matrix. If we look over here in our variable explorer, that's a pretty big variable. It's a 1001 by 1001 matrix that only took us, fraction of a second to compute. And we can actually take a look at that too if we want to go hunting for a specific value. It's a really big matrix, but we can scroll through it and see whatever we like. And one last thing is you don't have to create the plots necessarily using these functions within the actual script editor itself. If we go up here to the top, we've got this plot assistant, which is one of the helpful tools available. And we can actually pick some data and a style of plot. So if I just wanted to say model X and Z, I would need to actually go into our workspace. This is if you want to pull data from a specific file, or since it's already within this script that we're using, we can plug in our defined X and our defined, we'll just say Z. Since X and Y are the same, it would be a straight line. This actually, I don't believe will plot because, oh, it will. So kind of a wonky graph right there, goes all over the place. But what we'd be more interested in is maybe our 3D surface. So we can go down to our 3D patterns right here, and we can pick surface, and we'll change this to what we actually were trying to look at earlier, X, Y, and Z. And we'll plot it, and we get. So that's what I was saying earlier, where it shows up as a black line. Those mesh lines that kind of define the grid of the system are so close together that it's covering up the actual color scheme of the problem. But you can get around that by copying this plot command into the script editor and turning the mesh lines off, or just reducing the mesh itself. So that's all there is to some of the simple calculations at the beginning. So let's hop back over into our slides right here, and we'll get a little bit more advanced. So what we can do now is start looking at some repetitive tasks. So any sort of calculation or objective that needs to be done or calculated over and over again, you could use Excel, or God forbid you could do it by pen and paper with a calculator, which that would become a nightmare pretty fast. And Excel kind of taps out at a certain point when it comes to really large sets of data. And again, that's where an OML really shows its value. So for this example, I know this looks like a jumbled mess of equations on the screen, but we're going to be taking a look at the microstrip design equations. So these are just some of the basic textbook design equations for when you're first learning about some microstrip transmission lines. So what we have here, excuse me, you can see this is a really long equation, and then we've got this variable b that makes it even longer. And then what makes this even more complicated is that this the width of the conductor related to the height of the substrate, which equation to use is based on the output of the equation, which can become tedious and annoying pretty quick. If for example, you've picked your substrate and the height of it, and you plug in all your values into the equation, and you find out that actually W over H was less than 2. And you've just done all this calculation for nothing, and then you still have to go do the second one. So that's where we can hop back into Compose, and we can take these equations that we just defined up here. So we've got that variable b, and then our two equations, a and then the second equation. So all I've done here is defined some known constants, some parameters of our problem. So the frequency of the device, the characteristic impedance, and then this length and wavelengths. I won't go into detail because this isn't about how to design a wave or a microstrip. But a lot of times you'll hear that microstrips are designed in wavelengths of the device instead of a physical length. You then calculate the physical length once you determine the wavelength within the device, which is another calculation that you'd have to do, because in addition to calculating that W over H, you then still have to calculate W, the width of the conductor. Then you have to calculate your effective dielectric constant, your wavelength, surface resistance, your attenuation in the conductor and in the dielectric, and then of course convert all that to decibels, because that's probably what you're most interested in. And again, I apologize if you're not an electrical engineer, but basically, to make a long story short, there are a lot of steps. Anytime you change one parameter, there's a lot of calculations that you have to go through, including this big nasty one that could change based on which parameter you use. So you're not guaranteed to use the same equation every time. So all I've done here is plugged all of these calculations in, and I can run that, and almost instantly, based on knowing what the conductor is and what the dielectric is, I can get the conductor width, microstrip length, and the total attenuation in the device. So now I'm one step closer to actually going and fabricating this device if I was interested. Of course, I probably want to model further, more detailed, which I could make some more realistic changes to the equations in Compose, or I could design it in a 3D environment in FICO, which I'll touch on later. Again, since this is a Compose webinar, I won't spend really any time in describing FICO. But let's say we wanted to change a parameter in this right here, and I didn't want to go in and plug it in every time and run it over and over to see what the effect is, say, on the total attenuation. So again, I can kind of combine some of the stuff we've been talking about with vectorization. So right here, I say that I want to change the height of the substrate. So I've just defined it from over a range, keeping everything else constant, and then running through the calculations to see what the actual attenuation would be as an effect of the height of the substrate. So again, I'll run this and plot the results, and you can see from 0.5 millimeter up to 2.5 millimeters, we can see that attenuation go down with a nonlinear characteristics, which is what we expect with these equations being including exponentials and logarithms and whatnot. And this could be handy for a number of reasons, because what we're saying here is as we increase the height of the substrate, our attenuation goes down, but we can't necessarily just increase that forever, because we have to factor in other things. As the height gets bigger, the width gets bigger, the width of the conductor, that is. So then we're looking at perhaps a different length of the actual microstrip. All these change the footprint, the mass, the cost of the device. And so let's say we wanted to actually kind of optimize some of that. So what we can do is we can do some optimization in Compose. Now, I didn't prepare an example specific to this exact problem. This is actually one of the pre-made demos that comes with Compose. And I'll point out where to access those right now. So over here next to your variable browser, you should have a demo browser where you've got a nice folder of demos with all sorts of different helpful OML files that will kind of get you a baseline on how to begin approaching whatever problem you're looking at, whether that's using Python within Compose or this optimization problem. There's even some simple forms of machine learning. There's some clustering and some regression models. But we won't touch on all of that just because it is so extensive what is capable in Compose. But so, let's say we have some problem where we have multiple variables we want to change defined by some output. So that's exactly what we have here with this beam optimization problem that comes as a demo in Compose. So what we can do is say that we want to keep our stresses confined to a certain constraint, and we want to see what the actual physical parameters of these are. And we want to minimize the mass of the device while keeping all of these constraints in mind. So we can run this, and you see we actually get a little animation as it goes through the different values until we get to our optimal height and length of this beam. This is our cross-section look at it, and we've got some helpful outputs down here that we can code into the script to say, hey, I want you to print this out, and maybe give some helpful text as to what the number actually is. So again, a lot that you can do along the way within this one tool. So with all of that being in mind, I'll go ahead and swap back over to our presentation as we take a look at some of the other features available within Compose. So right here, we've got the ability to create graphical user interfaces, or GUIs, GUIs, whatever you want to call them. And you don't have to code it in HTML or Java or whatever it is you might be used to coding these in, because Compose has a built-in GUI for doing this all for you with a nice drag and drop interface, and then it will spit out the OML code for you to generate that GUI again in the future. And this could be useful for a number of reasons. Maybe you want to make one small change in the code, or pull something different in, and you don't want to have to go edit it in line every single time. You can make a GUI that would ask for a user input to do that for you and then run whatever the program is. And again, in a similar vein, maybe you want someone not as familiar with the work you're doing to be able to produce results still. Maybe, for example, you have an intern and you don't trust them to do everything by themselves. So you can write a script and make a GUI for them, and then they can just plug in numbers for you. And it will spit out the answers according to whatever functions you've already defined. So let me show you a little bit about how that works within Compose. So we've got this up here in the top, this UI designer. So we just can open that. Let me pull that over. And we get this designer interface right here. So we can make our window whatever size we want, and then we can start adding components in right here. So say we want certain text to be displayed at the top. We can drag that over and tell it what we want, you know, what this window is. This tool does such and such. We can also add boxes for users to type in right here in these edit boxes. We can add radio buttons if you have a list of options available. Maybe you've custom coded 2 different kinds of numerical solvers to some problem, and you want to be able to decide which one you're running with without having to, you know, comment out a chunk of code in the actual script. You can just set it up to where the radio button will pick one for you. And several other options. I won't go through all of them. The last one I'll go through is this push button option. This is, for example, where you could, you know, push your go button right here. I've plugged in everything into this GUI, and now I want it to run the program. So you could hit that button and it would run for you. So I won't go through the whole process of making one of these, but I will show you what it looks like after you've made one. So this is the automatically generated OML that is spit out afterwards. So it looks like there's a lot going on because I do have a lot of text boxes and user input on the example. But basically, this is just defining each element on the screen. It does all this for you. And you can go in and make whatever minor changes you want right here. If you want to change the font size or the color of something, or how bold a line is, or the exact location you want to move it a couple of pixels over, you have that option. You can do all that right here. And then we can actually define some functions to pull in some values and manipulate them based on whatever calculations you're trying to do, whatever your objective is. So for this example, what I've done is created just a simple little GUI for some 3x3 matrix calculation, kind of showing off a couple of the different features here. So we got some default inputs that we can click calculate, and we'll get our output matrix. And again, you see up here, I've defined that F is equal to A times B. So we have A and the max value, just showing off kind of what you can do after, you know, you've used some user input. But let's say I want to type in all my own values, then I can do that. So I'll just quickly go through and let's just count back down. And now we're going to say, let's use my values and let's calculate. So then we get a new output because we have some new inputs, and we see all that pretty nicely. We can clear all that out. So this is kind of a trivial example using building a whole GUI for matrix multiplication. But it just shows that the options are really almost limitless. It's up to you how far you want to take this right here. You can build a GUI to pull in outside files and you know, manipulate them in certain ways. It's up to you. There's a lot that can be done. It's a really powerful design tool that makes using Compose even it makes it more user friendly than it already is, which is really nice. So with all that being said, I'm going to hop back over to our PowerPoint. Let me just pull this up. And we'll move along and take a look at some more features within Compose. So we've looked at a lot of simple examples so far, and not to say that these are extraordinarily complex, but we'll branch out a little bit and see more of what Compose has to offer. So again, we can model some real world physics, and we can even animate motion, which I'll show an example of. And then something that I'm sure more of you might be interested in is the ability to solve differential equations within Compose without having to write your own numerical solver. So the example that I'll cover when we get to it is just this telegrapher's equation. Again, I told you I'd be a little bit on the electrical side today, but without going into too much detail, this actually should be telegrapher's equations because there's another one that shows the current. But basically, what this measures is over some transmission line or cable. Because of the resistance of the line, its inductance, which it'll have just being a current carrying cable, and then some conductance and capacitance to ground. All of these are really unavoidable in the real world, and we can start to model them at least at a high level in Compose with this equation right here, where we take all of these components in mind, and we can treat this as a differential equation and solve it. So let's hop back over into Compose. So first I mentioned that we have some physics. So this is a really simple, again, kind of trivial, but a fun little way to look at some motion or some kinematics in Compose. So here we're just dropping a ball from a height and we're watching it bounce. So we're assuming that the only force on the ball is gravity. We could make this more complicated by starting to incorporate some air resistance and starting to look at how that would behave. But for this first one, we'll just keep it simple. Initial height, this y1 of 10 meters and initial velocity of 0. We're not throwing it down, we're just dropping it. And all we're doing is, again, we're looping over the kinematic equation, and we're assuming that when it hits the ground, it bounces back in the opposite direction with 75% of its velocity, which might be a little generous, but it's good enough for this simple simulation. And then we can actually animate that using this draw now, which you've seen it before in some of the other scripts I've already shown, but really pointing it out now. We could, if we wanted to get this down to a specific time, we could incorporate a pause. So for example, if we knew that each step in our simulation was 0.1 seconds, we could pause 0.1 seconds and get an animation pretty close to real time. But this one, I just changed the step size and let it go with the duration of the loop itself. So it's not going to be exact, but it's close enough for today's purposes. So yep, you can see here, we just have our ball dropping. It looks like it's moving to the right. I didn't actually do any 2D or multi-dimensional motion here. It's still just bouncing straight up and down, but that's just as it moves through time to kind of show the progression of time here. Not really necessary, but it's what I went with on this specific one. It's a pretty short animation. You can see it bouncing, coming to a stop. But with that being said, let's take a look at the more complex telegrapher's equation and see how we can actually solve some differential equations in here. So again, I just plugged in some random values for resistance, inductance, conductance, and capacitance, and then defined the coefficients for each term of the differential equation as they were represented in the on the PowerPoint. So that middle term, the dv dt or del v del t, that had Lg plus Rc over Lc, we can define that all as one number here, which makes it a little cleaner for actually telling Compose how we want to solve this differential equation. So again, a lot of this is just setting up some of the space and time divisions. And then we can actually define our, set up our differential equation and solve it using the built-in ODE 45. So that's the big thing I wanted to point out here. Not so much the setup, but that solver itself. So once we've plugged everything in, this one little function does all the heavy lifting for us. And there's actually 5 built-in differential equation solvers in Compose. And they're based on a couple of things, which solver method you want to use, which numerical method that is, and then if the equations are stiff or not. So for this one, we use ODE 45. It's kind of the go-to. This uses the Runge-Kutta method or the Rung-Kutta, depending on who you ask. And then all we're going to do is plot it. Let me kind of explain the plots you're going to see before you see them, because one of them is animated. So there'll be 3 up here. The first one will be the x-axis will be the length of the wire, and we'll see the voltage signal in it animated over time. And then the other 2 will have an x-axis of time, and we'll see at one specific position, not over the whole range, what that signal looks like. So let me show you that, because it might be easier to see. So yeah, we have in that top one up there, that animation was the voltage signal at any given point. So that's what this bottom is. So at, you know, 1/10 of the way, animated over time. So if we look at one specific point, we should be able to see that value go up and down like a sine wave, like we would expect if you just keep your eye on one point. Kind of hard to see that it's sinusoidal that way, but it is. And then again, we've got our static measurements down here, or static, at least not animated. But here we've got our time from 0 to 15 seconds. And this first plot is right at the input of the voltage signal. And the second plot is right at the output of the voltage signal. So you can see, because of our parasitics, we've lost a little bit of amplitude, and there's a phase shift, which we'd expect. But now, thanks to this differential equation solver, we can actually visualize what that effect will be. And we can get more accurate by changing the time step, and we can change the length of the wire. There's plenty of options available to us. But this is a nice way to solve and visualize the solutions to differential equations within Compose. With that all being said, I'll go ahead and move along to one of the last big features of Compose, which will be our integration with other tools. This is where it comes in really nice, is you don't necessarily have to use Compose to generate whatever data you want to analyze. It could come from anything. It could come from an Excel spreadsheet, it could come from another Altair product, whatever you might be interested in, and then you can actually analyze that data in Compose. And another really nice feature is the ability to create code your own custom OML blocks and Activate. So if Activate just doesn't have what you're looking for, you can write it yourself and plug that in. And Activate, I know I didn't touch on that today. If you're unfamiliar, that's our kind of systems of systems, multi-physics, visual coding environment. It's a drag and drop environment where you can pull blocks in for physical, electrical, mechanical, digital signals, and implement control systems or analyze physical systems. There's a lot of availability there, but sometimes they might just not have exactly what you're trying to do within that tool. So that's where Compose could become handy. Excuse me. And kind of circling back to scripting repetitive tasks, we can do that with large sets of data from other models. So kind of looking at this waveguide again. So say we've done all of our calculations and design and Compose, and we're happy and ready to actually model it in 3D in FICO, which is our 3D electromagnetic solver. It does electric fields, magnetic fields, You can measure currents, voltages. There's a lot of availability there too. Again, I won't go in too much deeper what FICO is. Perhaps that'll be another webinar. But let's say we model this in that software, and we want to change the length of the device in small increments to see what kind of effect that has on the performance of the device. So we can actually use FICO and Compose in tandem here, because we can run in FICO. Again, I won't show it since that's not the focus of today, but we can run this model to change a certain variable over and over and run again using scripting available there to change the length of this device. So say we define this as a variable, this length, and we want to see it from 45 millimeters up to 55 millimeters. I believe those are the numbers I used. We can actually run that, and we can have it step, through those values. I just had it go one at a time from 45, 46, 47, so on and so forth to keep it from taking too long. And then we simulate it, and we can extract those S parameters and pull that all into Compose. So kind of brushing over the work in FICO, I'll just pull up kind of what I've done in Compose. So I've defined some of the stuff that I already told FICO, the frequency range that we're looking at the device, and then of course the range of lengths that we're interested in. Yes, 45 to 55. So then what I can do is I can pull, cycle through all those folders that I saved everything in, and pull out some results that interest me. So in this case, I'm doing S parameters. So that's one thing that you wouldn't be able to do in FICO is you would be able to look at each individual output, but it gets a little hard to compare everything all at once. So that's why we can pull Compose out and actually use all of this information at once. Oops, I didn't mean to type that. So we can pull all of these S parameter numbers that are extracted from FICO and plot that in 3D. So that's exactly what we've done here. And so we can see, if we kind of look at this head on, it looks like our standard. If you're familiar with S parameters, it looks like an ideal, almost ideal, waveguide or transmission line when we're looking at reflection coefficients. So this is that S11. Again, not going to go into RF details here, but more just to show off that I was able to pull that whole sweep of results out and plot them all at once as a function of the frequency, because each simulation in FICO has a range of frequencies, and then of course we ran that simulation over a range of lengths, and then we can look at the whole thing at once. So maybe all we care about is optimizing this reflection coefficient. We could find whatever the global minimum of this is right here. Visually, it looks like it's about this spot, so we can figure out what substrate length that is and what design frequency that's operating at. It looks like it's about 2.2 gigahertz. Again, a lot you could do there with that information. You could slice this if you wanted to get an idea of the bandwidth of each device. Again, it's really up to you how far you take this. There's a lot you can do with pulling data from other softwares and visualizing it on a larger scale. So that's really all of the really high level features. I did want to show you one other thing. This is kind of just for fun, since we do have a little bit of time before I'll open it up for questions. I think we have about 15 minutes left, and this will only take a moment. So this is something I actually coded, and we have a blog on our website where I talk a little bit more about this. But basically, we had, I don't know if any of you remember, Chipotle some time ago had some problems that just random puzzles that they posted online. And if you solved it, it was free food. So that's what that blog is about, using Altair Compose to get free food. But basically, they posted just this text right here on their app. And I thought pretty quickly that it was probably some kind of cipher, and I was hoping that it was a simple Caesar cipher, just the normal shift it by X number of letters. And I could have probably done it faster by hand, manually checking each one until I got a word. But I thought it'd be a lot more fun to do it in Compose. So basically, I pull in some text and compare. I cycle through the words and compare it to a dictionary of real words until the sentence is made up of real words. So it's a couple of assumptions here that the deciphered text is grammatically correct, or at least spelled correctly. But still, it's a fun little program where I can hit run. So a little window pops up saying entered the encrypted message. So let me just copy this right here. I'll paste that and I'll run it. And you'll see as it attempts to break the code, and then we'll break it. And you see that we had a cipher shift of 23. So digital menu exclusive tastes best when juniper berries bring flavor. That was when their carnitas bowls had juniper berries in them. So got a free bowl with that. And it took about 4 seconds. So that was just one last little fun kind of demo of what's available in Compose. Again, not super practical in the real world, but who knows? You might be able to decode something more serious than this using this language. So with all of that being said, I will open it up for any questions that anyone might have. I don't think anybody asked any questions throughout the duration today, but feel free now to put any in the Q&A section, and I can address them for everyone if anyone is interested. I don't see any questions yet. Let me just check. Yeah, no, nothing yet. I'll stick around for a couple more minutes to give you time to type questions if you have any. But if you don't have any questions, that's all I have prepared for today. And I really appreciate you coming. Thank you for attending and hearing what I have to say about Compose, and I hope it was helpful. Feel free to reach out to us at TrueInsight for any further questions you might have regarding Compose, and we can work with you to get something together. We can set up a meeting. Oh, it looks like someone typed something. Let's see. Oh, yes, it is very interesting seeing the capabilities. Oh. Okay, I'm going to go ahead and close that poll that I opened at the beginning in a moment. So if anyone hasn't answered, go ahead and plug in that for me. Looks like everyone who opened it has already. All right, I'll go ahead and end that. All right, well, it doesn't look like there are any other questions. I don't see any other messages anywhere. So thank you for coming. I'm going to go ahead and stop the recording. Let me pull that up.